What's this? Oh, because I have we were testing it this morning, so I had the sound muted so that we had it in the headphones and could tell whether it was coming through the headphones or the speakers. Okay, so just as a quick recap, so we talked about data representation languages last time. We kind of started off with the discussion like about HTML. So HTML, I don't know for sure it was our first well, actually, it definitely wasn't the first. CSV predated it, but maybe it was kind of our first modern data representation language that was widely accepted. All right, so because the internet kind of started off, and I mean, most of you aren't going to remember this, but because when you started using the internet was already a thing, right? Well, I was around when the internet first came out, and it was a fad. Who knows if there's going to be something real? Similar to whether it's VR now or that kind of stuff. It's like, oh, this is cool, but do people want it? Are people actually going to use it and that kind of stuff? And it was far more difficult to connect to the internet in the early days with your dial-up modem, and you had to find a provider. Providers weren't on every street corner like they are today. You had to find sometimes it depended on which neighborhood you lived in as to whether or not it was a local phone call to your local bulletin board system. And that's kind of where those MUDs were born, is in these bulletin board systems where, it would have 30 modems. And you would, so you dial into one of their bank of modems, you hear all the beeping and stuff like that, and then you're on this, effectively a network operating system, all text-based, but you're one of 30 users who could be on the system at once because that's how many phone lines they had coming into it. And you had a menu system that said, oh, well, you could do email, you could do web browsing, but all text-based web browsing, or you could play there was several different games on there, and one of them was like the MUD. It kind of started with that. So as things started evolving, as we started moving from text-based internet, and even in the early days of web pages, it was still HTML. So as these and the internet kind of started with this idea of several big universities who were trying to share data between each other. Okay, and one of them was the University of Illinois. And any of you have heard of this place called NCSA, National Center for Supercomputing Applications? Any of you heard of the web browser called Mosaic? Okay, so Mosaic, I think, was basically the first, let's call it, real web browser. And it was made at National Center for Supercomputing Applications. And I think it's at least fair to claim that maybe the internet was kind of born there. And the internet as we know today was kind of born there. And so this is in Champaign, Illinois, where the University of Illinois is. And so I was a lab monitor at National Center for Supercomputing Applications. I was a kid, so, well, I mean, I guess I was, must have been like 16, 15. I could drive, so it must have been 16 or 17, something like that. And so I worked there, and so I was buddies with the computer science grad students who were working on this. I thought I was buddies with them. I don't know if they thought the same thing, but who were working on the first web browser. So I was kind of they would give it to me to test in the lab. I have a little floppy disk with Mosaic on it when they existed, the actual floppy disk. But so it was kind of an interesting thing that, I have a little bit of a backstory where I was kind of there at the, not involved other than just I kind of maybe had early access to some of those things before things were available for early access on the internet. I had to physically be handed a disk to try it. But, kind of interesting stuff. But originally the internet was kind of made for these universities to share kind of, let's say, research information and stuff like that. So they needed to have some sort of consistent language to represent data as you were sending it from point A to point B. And you got to consider at this point in time, even though, University of Illinois is, a big major university that had lots of research dollars and stuff like that. So if anybody had a pretty fast internet connection by that day's standard, it was them, right? but it's still, by our standards, the internet was slow, okay, almost unusably slow. Like the internet in its fast speed was just slightly faster than our internet is right this moment. So, and we don't have internet right now, so what really wasn't very good. So they needed to have a way of how do we send textual data, because images and stuff are really too big to send in any sort of reasonable amount of time. How do we send textual data from point A to point B in a consistent format, so we don't have to go and teach University of Wisconsin, the correct little, secret code that they have to use to send data back and forth between University of Illinois. And that's where this idea of HTML came out, this tag-based language, which then kind of evolved into XML, which is Extensible Markup Language, is what XML stands for. And so, the idea is that you could say, well, I want tags like HTML, but I want to make my own tags. I want to represent patient records or something like that. But we saw last time, we looked at an example of XML somewhere, didn't we?
Yeah.
It was in here. I just changed it. So somewhere in here, I would have like a couldn't connect to iCloud. So do I have to specifically say I want to edit a copy? Set the magic. Couldn't connect to iCloud. That's pretty unfortunate, isn't it? It seems like they could, let's close this, let's reopen it, and then we'll do the edit a copy thing, and then we'll see if it decides it wants to save it later. Okay, fair enough. Oh, it's showing up as a copy, but I guess we'll just roll with it. So I might have something that looks like a patient record. And then inside here, I might have a F name, Mike, / F name, and I might have a L name, Littman / L name, so on and so forth. So we can imagine this gets pretty tedious, and we kind of saw last time it looks like I erased it or wrote it a different way or something like that. But very little data is actually represented here, right? A majority of what we have in this these couple of lines is descriptive information about what our data actually is, what it means, right? The majority of this is tags. So we would say, yes, this solves the problem. So now let's think about it this way. How much data does this take to send? So we kind of got to roll back and really think about the nature of data. So back then, in the early days of the internet, we were using an older character set. What character set's popular today? We talked about it earlier in the semester. Okay, ASCII is the one they used back then. Today we use Unicode. Unicode's a superset of ASCII. So the first 256 characters of Unicode are the ASCII character set. So ASCII is an 8-bit character set, which means every single character that we're going to represent in ASCII takes up 8 bits of space. So each of these characters takes up 8 bits of space. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. So let's just kind of duplicate that. So we'll say 28, 56, 65. We'll say it's 65. We got 65 characters there. I've counted them verbosely. All right, so at 65 characters, that's times 8 bits per character. So that's 65 times 8. That's 520 bits. Okay? And if you want to think about that in terms of what's that in terms of bytes? It's actually 65 bytes, right? So times 8 divided by 8, because there's 8 bits in 1 byte. Okay, so we have 65 bytes of data because every character is 1 byte big, or 8 bits big. All right, so 65 bytes. Now, we view 65 bytes as not necessarily being very big, right? We want to kind of convert this into, so we divide that by 1,024, that's 0.06 kilobytes, divided by 1,024, that's 0.0000619 megabytes, so on and so forth. So by today's internet standards, that's a pretty small amount of data. We would guesstimate that sending 64 or 65 bytes across the internet would take no time whatsoever. But now we got to go back and we got to say, okay, well, back then, maybe we had something called like a 300 baud modem. 300 baud modem. So a 300 baud modem would transfer stuff at 300 bits per second max. Okay, it was a theoretical max because the two modems, the modulator, demodulator, is using a analog telephone line, right? So we got a line between, so this is kind of a little networking lesson. So you have your old analog telephone lines. Now, computers, they were digital back then as well. Okay, our computers today are digital things. Computers back then, also digital. So now you have these digital animals in either end with an analog thing between. So the reason you needed that modem is to convert between digital and analog. How do we take the analog signal that was traveling over the phone line, convert it into something that the computer can now understand? Similarly, when the computer sends something, how do we convert that digital signal into an analog signal that can be sent over the lines and received by another modem and converted back into a digital signal, right? That's the whole purpose of those modems, is to convert the signals to and from what the computer understands and what can be transmitted over that line. We don't have that issue today, and that's actually kind of an interesting thing. So how many of you have a cable modem at home? Or a DSL modem at home? Okay, so if you have an internet connection at home, if you have cable internet, a cable modem, they give you a box, and they call that a cable modem. The reality is it's not doing any conversion. So it's really not a modem. But everybody's called them modems for years and years and years and years. So how do you connect to the internet? You use a modem. So that's what they call it. But it doesn't have to do that connection because it's digital everywhere, right? When you're using the cable network, it's going over, well, it appears to be coaxial cables at your house. I think most of them are fiber, somewhere in the middle, but not analog. It's digital stuff point to point, all the way across. So we're not having to do the conversion, but so what's the purpose of those modems, do you think? The cable modems. Why do we need those? Similar purpose to why we need the, if you have DirecTV or you have Uverse or cable TV, why you need a box, a set-top box. I mean, there's kind of many purposes, but what's the main reason that you need those things? I mean, a lot of our TVs have inputs in them. We could just show channels, right? But those boxes decode. Why are our TV channels encoded? So you can't steal it. It's all about money. Okay? Cable companies got to encode all their video signals so that you can't steal their TV. So then you got to come and get a box. Now, that's a real racket, right? Then they make you rent the box. It's like, so you can't steal our stuff. If you actually want to have it, you got to pay us money. But even paying us money, I mean, that's the real kicker. You can't say, I don't want to rent the box. You need the box. I get it. I don't want to rent it, but I still want the service. You got to rent the box. Why don't they just wrap that into your, but they work off of perception that you think you need the box for something extra. Like that's how you get the super high definition channels, or it is also how you can do the request for like pay-per-view type stuff, but even that's changed. Historically, you used to need the box because cable was one way. It was a broadcast technology, wasn't a two-way stream. So even in the early days of cable modems, if you got a cable modem internet connection, you also needed to have a dial-up modem. The dial-up modem, what are you're messing with? You're paying attention to me, or you're paying attention to what's on your computer screen? He was paying attention to the computer screen, wasn't he? Okay, so in the early days of cable modems, we had you had to have a dial-up modem as well as the cable modem because you couldn't make that request. You couldn't type in www.google.com as if it existed back then. You couldn't type that in and actually have the request go out over your cable modem. The request went out over your dial-up internet modem. The download then came from your cable modem because your cable modem was a broadcast technology. You could receive it. But the reality is usually what we're downloading is far bigger than what we're requesting, right? Which, we just talked about this thing taking up 65 bytes. All this information is that about the same thing as like www.google.com might take up. So we're going to send 65 bytes this way, and then when we download the website, maybe it's 200 kilobytes, something like that. A lot bigger, right? A lot more stuff comes back. So we want our download to be faster than our upload. All right, but even in the early days of these set-top boxes with on-demand, you had to make the request through a modem. So you had to plug a telephone line into the back of your cable box. Any of you remember ever having a setup like that? Where you had a telephone line into the back of your cable box as well? Might be before your time. But in any case, that's how you requested the pay-per-view, and then the movie would download through your thing. But you don't have that anymore because now the cable coaxial network is two-way. You can make a request, you can get your download, no problem. You can even do this right from your TV. But they want you to have the box so that they can charge you for the box, they can charge you for the service, and they also can control shutting you off. Does that make sense? They use it to uniquely identify your home. So when you go, if you want to use how many of you use your own cable modem or something like that for your internet at home? So you don't rent the box, you have your own, right? Okay, so when you got that, you had to go and call them up and you say, I have my own cable modem. They made you bring the other one back, right? So they would take it off your bill and not charge you the $8 a month for it or whatever. But then you had to give them this thing called a MAC address, right? Because that cable modem that he bought at Best Buy or whatever, it has a unique network identifier. They had to add that MAC address to your account at Time Warner or Spectrum or Comcast, whoever it was. They had to add that MAC address to the account so that when your modem requested access to their internet, it matched up to your account and made sure your bill was up to date before they'll release the internet to you. Does that make sense? That's kind of how all this stuff ended up working. So this idea of two-way communication, this is stuff you'll go into a lot more depth in this in a networking class, but that was kind of, the networking as it relates to internet in 10 minutes. That was that little piece there. But the point is that back then we had much slower internet connections. So go down to maybe we have a 300 baud modem. Now, in actuality, when the internet was first kind of becoming a little bit popular, the modems were faster than 300 baud. We went from 300 to 900, from 900 to 1200, then to 2400, 4800, 9600. Then we had 14,400. Then we had 28,800, so the 28.8 modem. Then we had a 33,600 modem. Then you had the 56K modems, 56,000 modems. They were the rocket ships. Yeah, and then you would sit there and fiddle with it because that was a maximum speed is the 56K. So 56 kilobits per second. So 56 kilobits divided by 8 is 7 kilobytes per second. That's how fast you can download stuff, is 7K per second. Slow? By today's standards, this was like highly in demand. People would line up to buy their modem back in those days. But you didn't always get 56K because all that beeping when your modem is connecting to, you've heard that at least on a soundbite at some point, all that stuff. Okay, that's called handshaking. And what's actually happening there is the two modems. So this modem's talking to this modem. All right, you're over an analog connection in the middle. Okay, presumably an analog connection in the middle. So these two modems are talking to each other, and what they're doing is they're negotiating what is the fastest speed that we can talk to each other without screwing up. We don't have that problem anymore today because we have backup. Okay, we have our own secret service on our networks. We have something called TCP/IP. We've all seen those words before. TCP/IP. What is TCP/IP? So even those of you who work in IT and all this stuff, you've seen this all over the place. It's like, oh, just go in and change your TCP/IP settings, but you don't know what it means. You know what it's for. Anybody in here know? How many of you have seen those characters next to each other? TCP/IP. Most of us at some point, right? Okay. So what TCP/IP is, at its heart, is error correction. It works on packet switch networks, so it divides your data into smaller chunks. So it basically says, okay, here's the data you want to send. Rather than me sending it all of it at once, I'm going to put it in little snowballs and kind of throw one snowball at a time. But what TCP/IP does on the other end is it guarantees that not only your data arrives, but also gets reassembled in the same order it was sent. And if something gets messed up, so if there was a collision in the middle, so one of my snowballs gets destroyed, okay, one of my packets gets destroyed, I then get notified that I need to resend that packet. So I have my original data here. It's like, oh, okay, here's that packet, throw that again. So it eventually gets there. Does that make sense? So we make this assumption that errors might happen. We don't have to worry about kind of a speed where we won't mess up. Okay, so in real life, if we're, let's say we're handling, I don't know, what's something that might be like dangerous to drop that we don't want to get too violent. Glass. Okay, but not like exploding glass, but just, So if you're handing somebody like some like fancy crystal, okay, something expensive, something like that, okay, you're probably not just going to toss it to them, right? Okay, this is a choreographed move where okay, do you got it? And then that's when you let go. So there's a speed at which the two parties have negotiated that we can safely pass this crystal off to somebody else, right? Okay, that's the old dial-up modem world. How can we move stuff from one point to another point without screwing up, without dropping the glass, that kind of stuff? Okay, but now, with our modern day internet that's protected by TCP/IP, we're just going to whip that glass at you. If you drop it, got another one right here. Heads up, you just keep going until it finally catches it. So TCP/IP, it's great. You might resend the data 50 times, but our internet's our network connections, which are different than internet, right? You can have a network connection. For instance, here on campus right now, our internet's dead, but I would assume the network drives are still mapped. You can get to, in fact, I think you can get to my.cuw.edu because it's a locally hosted site. Blackboard is actually hosted off campus, so you probably can't get there, but I think it's hosted off campus, isn't it? Pretty sure. You can definitely get to my.cuw.edu. At least I was able to do it in my office because that's a site we host here on campus, so we don't have to leave campus to get to it because we have our own DNS servers. It's a whole nother internet thing. Let's not go down that path too much. At some point, take the networking class. We have a networking class, don't we? Yeah. If you're an IT major, take the networking class. I think it's 440 is the course number. Really? But you're on the Wi-Fi. I was able to connect to it over wired in my office. So it's possible the Wi-Fi... Yeah, but regardless, there's a rationale behind that. But this is kind of giving an argument that, one thing that we have with a lot of computer science students is they come here and they have this perception that, oh, I'm really good with computers. And you might be. I can give you any sort of, wireless router or something like that, and you could set it up, right? You might be good at all that stuff, but you don't necessarily know how it's working under the hood. That kind of makes sense. So that's where computer science education comes in, is filling in that theory. Now, you might be able to go your whole career and not know what TCP/IP means, but that doesn't mean you should. Because I think what's happened now is things have become so automated that, we don't need to know how some of these things work until there's a problem that having that under the hood knowledge benefits you in solving. So whatever's going on with the campus internet today, it's probably going to end up, unless it's something stupid like somebody cut a wire or something like that. Huh?
No, he had nothing to do.
it's probably going to end up being solved by somebody who has some underlying understanding of, it could be that we're under a denial of service attack or something like that, where, our external traffic can't get out. So they're going to have to start thinking about our packet switch networks, take one router offline, put another router on, and under a different IP address, reconnect it up so we're no longer a target, all sorts of stuff like that that requires having an underlying understanding of how this stuff works, right? But now, punchline is, we needed a way when network speeds were far slower than they were today, especially because even if you had a 56K modem, you might have only been able to connect at 28.8, half the speed. If there was a lot of line noise on that analog connection, okay, because now we're passing that piece of crystal and we don't have TCP/IP to protect us back then. All right, so we need to send this stuff slower. So now we had to think about, well, how do I send information from point A to point B using some sort of standard? So maybe it's an HTML-based standard initially. That's how we sent these web pages from point A to point B. Such that our data gets described. It's a descriptive language. We're marking up our data. You can look at the data and see that, oh, I must be looking at a thing here called a patient record. F name, that probably means this is the guy's first name. L name, this means this is the guy's last name, so on and so forth, right? So it's added some semantics to our data at the cost of making our data larger than it used to be. But if we had just sent Mike followed by Litton and no spaces or anything, kind of the most compact way of sending that data from point A to point B, perhaps a human being could look at it in that particular case and figure out that that's a first name and a last name, right? A person, because we're smart, right? But even we can pretty quickly come up with examples where you wouldn't necessarily know that what the data meant. So let's say that I sent you 30 phone numbers in a row, not formatted as phone numbers. You just had the numbers. You didn't have the little parentheses or the dashes or anything, just numbers. That could be social security stuff. It could be phone numbers. It could just be numbers. You might not know there's 30 of them. It might just be one giant number. We don't know. So we need that meaning in order to decipher the information on the other end. So we needed a way of marking up our data to get it from point A to point B in a way that was usable. Fair enough? Okay. So now let's start thinking about the amount of time it would take to transmit this. All right, so would we say that this is a pretty small amount of data that we're sending here? Small amount of data. I mean, basically almost useless data. Can we imagine that back then? I mean, it's not like we're talking caveman days, right? Where we had, we were just transmitting our name or something. We had stuff. This was made for transmitting like research and things like that. So, this represents a very, very, very tiny amount of data that might get sent. So is it completely unreasonable for us to send 100 times this amount of data? 6,500 characters? So that's 6,500 bytes. All right. And I mentioned that we can send, using an older modem, just to exaggerate this a little bit, because this was the modems they were using in the early days of this. Let's say we were sending that over, and even earlier than this, they were slower than this, but let's just say what was called a 300 baud modem. Baud is short for something called BPS, bits per second. All right, so 300 bits per second gives us how many bytes per second? 300 divided by 8, so 37.5 bytes per second. That's 37.5 bytes per second. 6,500 divided by 37.5 is 173 and so 174 seconds. All right, so we have 174 seconds divided by 60, so almost 3 minutes it would take to send that information from point A to point B. Now, that was amazing back then, because this is before we could send any data. I mean, this was replacing us sending the information in a envelope, right? Waiting for them to get it on their end and read through it or have somebody type it back in, right? Now, computers did already exist, so you could have sent them a floppy disk in the mail, have them receive the floppy disk, put it in the computer, now they have the data. Okay, so we weren't so archaic. But that's still, I mean, mail today takes at least, 2 days, a couple days to get from central Illinois to central Wisconsin? Something like that. Maybe it's 1 day, but not 3 minutes. Right? Not 3 minutes. Even by plane, it's not 3 minutes. So, the idea here is this might have been a 3-minute turnaround for something that 6,500 characters isn't that big. Right? I mean, what do we have? 80 characters in a standard line? How many lines are on a single page of text? 600 lines? That sounds way too high.
No, I mean words.
Like if you write a term paper.
Like 600 words.
Okay, 600 words a page. That's fine. So I'm just thinking more of the number of total lines. So you think let's use 50. Use 50. That's going to be close enough for us to get a feel for this. That would have been something that we would have known years and years and years ago. How many lines were on a single typed page because that was meaningful. Now it's not meaningful, right? Yeah, we could Google it, but that's true. So we have 80 characters, and we decided by 50. So we have a maximum of about 4,000 characters we can squeeze on one page. If we have no spaces or anything like that, just characters. If I just sit there and hold the A key, I can get 4,000 characters on one page.
Do spaces count as characters?
Sure, they do. They do. All right, but just from the maximum amount of data as viewable by a human. You can say 4,000 characters on a page. So we're sending more than one full page. So a page and a half of just pure data. Now we're thinking about, we need to give meaning to this data. So if we think about writing the maximum amount of data on a full page, but now we need to, we saw here how much of this is actually our data. Not much. Not much of this was our data. So let's be nice and say, 20%? So 20% of that data, 20% of the stuff we sent is the actual information. A lot of it was structured. All right, so that means that if we go off of that, on those 4,000 characters on the page, only 800 of them actually meant something. The rest of it provided the semantics for that data. What was the first name? What was the last name? What was latitude, longitude, coordinates, whatever, stuff like that for your research. So we start seeing that now we're sending a lot of fluff, correct? But we can still send it. So we even had 3-minute turnaround time. That's great. I mean, this was amazing to people back then. This is, not so dissimilar from, the telegraph and telephone and things like that, where we're able to start doing some things like that. And now we have these computers that have become so amazing and so useful in in industry. How many of you have seen the movie Hidden Figures that came out somewhat recently? Okay, kind of a cool movie. It's the I think Grace is going to have, I'm guessing it's going to be next semester now, obviously, but sometime they'll have a movie night where it's, because it's very much about women in computers, where it's and specifically in this one, it was a group of black women who worked at NASA. And basically this was back during the time when even the bathrooms and stuff were segregated, right? Well, this one lady was basically a math genius, and they needed somebody to crunch numbers, so they sent her down to the, all pretty much white male group of NASA scientists that are trying to send these people into space. And this is based on a true story. So she was doing this work. Well, at the same time, this is kind of when IBM was first rolling out computers. Okay, so kind of what happened during this movie is it started showing that the computer could do so much more work. We basically made the human beings who were calculating stuff antiquated in terms of speed and stuff like that. But it was just, so we already were in a world at that time where computers had already become a thing. But having those computers talk to each other wasn't necessarily appreciated yet, right? We could value that we had this thing on the desk that could do kind of like what a calculator could do, but on steroids. And we could program it to do so much more than that, and we couldn't really see beyond what we could imagine. This is kind of the, human, innovation type stuff. And this is kind of, why I'm more recently so excited about this VR stuff, just thinking about what ideas are we going to come up with VR in 2 or 5 years. Right now it's gimmicky, right? It's kind of cool games. You got some cool experiences. You try it for a little bit, but then it becomes not old, but less impressive because like, oh, I've already tried all this stuff. But in 5 years, it might be very much part of our world. So we'll see. But in any case, sending data in relative real time in a couple of minutes between 2 points was amazing. I mean, this was a big deal. But we're already seeing that the amount of data we might be sending, so in this case, a page of data, a page of information, if we had to mark it up, times, so that is 4,000 bytes. And we can do, so that's divided by 37.5, so that's bytes per second. So that's 106 seconds divided by 60, so, just under a couple of minutes. 1.77 minutes per page of text that you're going to send. All right? But still way faster than mailing it. And certainly, we were already seeing that internet speeds kept getting faster and faster and faster. And now you start getting up to like that 28,800 speed, which was, let's call it middle of the road. So 28,800 bits per second divided by 8, that's bytes per second, 3,600. So now we're talking about sending that one page of text in just a little bit more than a second, right? Now we're starting to talk about something that maybe humans don't mind. 3 minutes, hey, this is amazing because it's faster than mail. Then that kind of gets old, right? We're never happy. How many of you remember the time when you were really impressed with your internet connection, and then sometime within 6 months, with the exact same internet connection, you thought it was the slowest thing ever? We're never happy. I don't care what internet you have, right? What's the current cool kid in internet? Yeah, Gigabit Internet, right? We have it down in Milwaukee now. AT&T has Gigabit Internet in Milwaukee. Google has Gigabit in several different places. So, Gigabit, that's 1,024 bits per second. That's gigabit. Well, actually, it's more than that. That's 1,024 gigabit is 1,024 times 1,024, that's megabit, times 1,024, that's kilobits, times 1,024, that's bits. So it's that number of bits per second. All right, so we take that number and we're going to send our 4,000 bits. So 4,000 divided by this whole big number. So that's seconds. I won't do the conversion to minutes since we don't need it. All right, so we can send a page of text using Gigabit Internet in 0.000000036 seconds. No time at all, right? It's a fraction of a fraction of a fraction of a second. So that's the current cool kid. How long is that going to stay cool? Because what's going to happen now that we have, so gigabit is starting to get into places. Milwaukee's kind of considered a second tier market. It's not a small market, but compared to New York City or Los Angeles, it's small, but it's bigger than Podunk, wherever. Okay, so it's already in the secondary market. So eventually it's going to be in most of the country, right? It'll be commonplace. So then what happens? The applications increase to take advantage of it. No longer are we going to be streaming 4K. Now we'll be streaming 8K video. Okay? No longer will we be limited to the amount of data your video games can send back and forth. So we'll just start sending more data back and forth to the point where now we start pushing on that technology. We can't make it go any faster. Start seeing some of the issues here. Okay, so a goal we had back then was we need to have our data be structured, but we need it to be structured in such a way that it's at least not adding too much extra stuff to our data. So we kind of have an appreciation for now how it connects to time when we think about sending this XML-based data across. So what we'll look at next time is how do we write this equivalent line in something called JSON. And then we're going to teach our objects how to export themselves to JSON. All right, so we'll teach a room how to, print out a string that is the JSON representation of itself. So you kind of see from a programming perspective how we can tell our programs to, dump themselves in JSON, because what we might do then is after we build out our dungeon, we could tell our dungeon to show us the JSON version of itself. Maybe we store that somewhere, so the next time we start up the thing, we could just feed it that JSON and it recreates our dungeon instantaneously. Make sense? Yeah. So you have an hour and 50 minutes to create that. All right, so no homework this time because I haven't given you enough stuff yet. And so actually, we'll probably end up writing it in class next time. And then we'll talk about the final. But the general thing, final's an hour and 50 minutes, covering everything we've done in the semester with a focus on stuff we've done since the midterm. So go through the slides, look at the stuff you've done for homework since the midterm. I'll kind of flip through quickly and give you the highlights, but the emphasis will be on the stuff we've done since, but clearly you're going to have to do if statements and that kind of stuff.
It's going to be like the same outline as...
So, it'll actually be pretty much 10 questions. So there should be no time stress because it's going to be designed to take about an hour, but you can have the full 2 hours. I don't care. Is it? Okay.
Came back up like 5 minutes before class ended.
What time is the final?
I have it written down. Let me.
10:10 on.
I think is it 10:10 Tuesday?
10:10 Tuesday?
Let me confirm for you. Hold
I
on.
think it's Wednesday actually.
Yeah, it's not. It's 10. It's 10. It's 10:10 on Wednesday.
All right. It's 300 on Tuesday.
Yep.